Good day, viewers. Once again, welcome to our today's online teaching series. We have a very interesting question here that state the following rules. Number one, HUND'S rule of maximum multiplicity, and number two, we have all BAU'S rule. Thus, explain electronic configuration. Now let's go there. So state the following rules. Solution. Let's take a look at HUND'S rule. Now, both rules, HUND'S rule and BAU'S rule, are rules used in filling electrons into the electronic blocks of an orbital. So let's start with the HUND'S rule. HUND'S rule, what is the statement of HUND'S rule? It states that electrons must fill degenerate orbitals singly before pairing. I will explain. Number two, all BAU'S rule. All BAU'S rule states that not more than two electrons should or can occupy each electron block. Now let's use a simple narrative to explain both HUND'S rule and BAU'S principle by taking a look at the electronic configuration of just three atoms. Let's take a look at number one. Write the electronic configuration. Electronic configuration of one, carbon. Let's take a look at carbon. Number two, let's take a look at potassium. And number three, we'll take a look at the atom zinc. Now, let's start with carbon. Carbon has an atomic number of 6. Potassium has atomic number of 19 and zinc atomic number of 30. Now, let's take a look at carbon. For carbon, remember in our previous series we said that we start with the 1s. 1s2, we have the s as maximum of 2 electrons. We have 2x2 and we have 2p2. Now, from what we have here now, using this to explain HUND'S rule, here I have my first and lowest energy level, 1x2. Now from where we have the 2 electrons, one spinning up and one spinning down. Please, we should understand that whenever you see 1 electron spin up, it means plus. 1 spin down, it means minus. 1 all over 2. So this is the spin quantum number of what we have here now. Now we have here the next energy level is the 2x energy level. For the 2x, we have 2 electrons, 2x2. You also give it 2 electrons because it is completely filled. 2 electrons, we have plus or minus 1 all over 2. Now the next we have the 2p. Now when you come to the 2p, we know that the p from our previous class has 3 electron blocks. We have the px, py, and pz. This is what we call degenerate orbital. We have 2p2. These are degenerate orbitals. Degenerate in the sense that they are of equal energy level. Just like in the school, you have JS1, JS2, JS1A, JS1B, JS1C, and JS1D. They are all of equal energy level. So according to HUND'S rule, it says that they must be filled singly. Because if you obey BAU'S principle by saying that not more than 2 electrons, you will do something like this. And if you do something like this, you are wrong. You have not obeyed HUND'S rule, you just obeyed BAU'S principle. So therefore, to fill in this, you attend to it singly and you take the next electron to come here. So what I have here now is the electronic configuration of carbon. Let's take a look at potassium. Now when we come to potassium has atomic number of 19. Potassium atomic number is 19. Written as 1x2, 2x2, 2p6, 3x2, 3p6, and 4x1. What we have here is the electronic configuration of potassium. Remember in our previous class we also said, here now you can get the group and period potassium belongs in the periodic table. If we take a look at the numbering here, the highest coefficient here is 4. So you find out that potassium here belongs to the period, which is the highest coefficient. So potassium belongs to period 4 of the periodic table, and the superscript to the highest coefficient is this. So it belongs to group 1. So the superscript is the group 1. Let's take a look at zinc. Now in zinc, I want to explain something different in zinc. Zinc is a transition metal. And transition metals are metals that lies between group 2 and group 3 of the periodic table with some kind of special characteristics, such as number 1, they show colors in solution. For example, copper is blue in color. We have iron 2, it is green in color. Iron 3 is brown in color. You have your manganese. Manganese 7 is purple in color. You have manganese 2 pink in color. So they show different colors. And the reason why they show these different colors is because of their incompletely filled d orbital. But for zinc, take a look at zinc with atomic number 30. Zinc has atomic number 30. You see it as 1x2, 2x2, 2p6, 3x2, 3p6, 4x2, and 3d10. Now compare this to copper. Copper 1x2, 2x2, 2p6, 3x2, 3p6, 4x2, and 3d9. Now see the reason why copper will show color in solution. The d orbital here is supposed to have 10 electrons complete to make it atom shell. Complete is 10 because the d orbital carry maximum of 10 electrons. But here you can see that it is not completely filled. Now because it is not completely filled, it means that electron can be excited from the 4x into the 3d. So this electron intertransmission results in the formation of colors in transition metal. But when you come to zinc, that position is not there because the 3d orbital is completely filled. So it means that there can't be any form of electron intertransmission. So zinc, a transition metal, shows colorless in solution because at the level of the 3d, it is completely filled. But however, copper, chromium, and other transition metal, because of their partially filled 3d orbital, they show color in solution. With this now, I believe justice has been done to the question HUND'S rule, BAU'S rule, and electronic configuration. Remember, electronic configuration is the arrangement of electrons in an atom, and that is what we have done. Please take advantage of this video, like my video, share, comment. If you have any problem, just drop it down in the comment section and it will be tended to. Bye until we see in our next episode.